All right, hey everyone. Today we're going to do a little radicals review. This should be something that you remember from Algebra 2 because this, is the Algebra 2 review unit. But for those of you that don't remember your rules for radicals, today we are going to go over them. All right, let's get started. Okay, so first we have to talk about, like I said, the rules for radicals. So there isn't that many, but we'll start with just going over these first, like I said. So here we go. Roll up my sleeves and get ready. So this first one is basically the rule of inverses. So if you are taking the nth root of something to the power of n, it simplifies to just the number itself. So we see this all the time when we have the square root of x squared. So let's just do that one. So if we had the square root, right? Now you don't have to write the 2 on the outside, but for this example, I'm just going to do it, right? So if you have the square root of x squared, the square root and the square are inverses of each other, so they kind of cancel each other out. And what you're left with is just x. All right, so that's the first rule of radicals. Like I said, it's kind of like the inverse property. All right, the second one is our multiplication rule. Now this works forwards and backwards. So if you have two numbers that are being multiplied together underneath a radical, you can separate them into two separate radicals. You can also do that in reverse. So if you have two radicals being multiplied together, you can combine them to make one giant radical. And this is going to come in handy when we're doing a lot of simplifying. So let's take a number example. So let's, for instance, say we have the square root of 27. Well, we want to simplify this if possible, right? Our goal is always to put something in the most simplified form. Well, in order to simplify something under a square root, you have to have a perfect square. So I want to ask myself, what perfect square can be multiplied by something else to make 27? So you start thinking, so what are your perfect squares? Well, 1 is a perfect square, 4 is a perfect square, 9, 16, 25, 36, 49, blah, 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 so on and so forth. So for 27, the biggest perfect square that's going to be divisible into that is 9. So I'm allowed to rewrite the square root of 27 as the square root of 9 times 3. All right, well, using this multiplication rule, I'm now allowed to break these two apart and write it as the square root of 9 times the square root of 3. And then I can simplify because I know that the square root of 9 is just 3. So I'm left with 3 and then square root of 3. All right, and like I said, it works the same backwards, right? So if you had the square root of 9 times the square root of 3 like separate like that, you can merge them together to get the square root of 27. And we're going to see both of those instances once we get to the example problems. So that's your multiplication rule. All right, the next one is our division rule, and it works basically the same way. So if you have one giant fraction underneath a square root, you are allowed to separate the numerator and the denominator into their own radical, like they have in that notation. So here would be like a numerical example. So if I had the square root of, say, 4 over 9, well, 4/9 itself, just as a whole, doesn't have a perfect square multiple in it. But 4 by itself is a perfect square and 9 by itself is a perfect square. So it would actually benefit me to separate the numerator and the denominator into their own radicals. So that's what I'm going to do. And we're allowed to do that. So square root of 4 separate from the square root of 9. And now we can simplify each of these radicals separately. So this becomes this 2, because that's the square root of 4, over 3, which is the square root of 9. Now, both the multiplication and the division property that we just looked at, those only work for division and multiplication. You cannot do this with addition or subtraction. So for instance, if I had, like say in my example, I had the square root of 9 plus 3. You cannot separate those into the square root of 9 plus the square root of 3. That's not how it works. All right, so these two properties only work with multiplication and division. All right, so just be careful. Don't try and do weird stuff with them. All right, so our only subtraction and addition properties are these ones we're going to see below. And this is kind of like a combining like terms situation. So if you have two different terms that have the same radical, so the same number underneath that square root or cube root or whatever it is that you're working with, you're allowed to combine them to make it into one term. All right, so for instance, if I had 3 square root of 7 plus 5 square root of 7 minus the square root of 7. All right, all three of these terms have a square root of 7 in them. So just like if I had 3x plus 5x minus 1x, I would be able to combine all of them to 1 because they were like terms. These are also considered to be like terms because that square root of 7 is the same, right, for all of them. So I can actually now combine the numbers out front and make this all into 1 because they have that same square root of 7. All right, so I can just do 3 plus 5, so 8 minus 1, 7. So this becomes 7 root 7s. And that would be my final answer. All right, so this only works because they have the same square root number. If the number was different, then I wouldn't be able to combine them because they wouldn't be like terms. All right, and so our last rule that we have is one that I know a lot of students struggle with in Algebra 2, and that's converting a fraction exponent into a radical. All right, so anytime you see something that has a fraction exponent, it just means that it's something with a radical in it. But yeah, so the most common one that you're going to see is things to the power of 1/2. So if I had x to the power of 1/2, that's the same as saying I have the square root of x to the first. All right, so the main thing is this number on the bottom will always match the number that's on the outside of the square root symbol. That's called your radicand. You don't need to know that, but it does have a name. So the number on the bottom of the fraction is going to go on the outside of your square root, and the number on the top of the fraction goes with your number underneath the square root or radical sign. It doesn't have to be a square root. All right, so if we have this x to the 1/2 here, that's the same as saying we have the square root of x to the first. All right, so that's a really common one that you're gonna see. All right, so if I mean, it works like even if we have like different ones, right? So if you had x to the power of 2/3, right, that would be the cube root. So the 3 is what's going to go on the outside of x squared. All right, so yeah, we'll talk about it more. This comes up a lot when we do our exponential and logarithm unit. But if you see that you have a fraction as an exponent, it does mean that you have some kind of radical in your problem. All right, so those are the rules for radicals. Now we're going to talk about something else that comes into play when we are simplifying, and that's called rationalizing the denominator. So we all know that sometimes math has real weird rules when it comes to simplifying. And one of those rules is you're not allowed to have a square root in the denominator of a fraction. All right, so I don't know why this is a thing. I don't know who made it up, but it exists. All right, so not allowed to have a radical in the come back. Where did you go? There you go. In the denominator. All right. So if we have a problem like this, where we have something, say, like 3 over the square root of 5, we are not allowed to leave this as our final answer. We have to find a way to get that square root of 5 out of the bottom of the fraction. And we're going to do that by what's called rationalizing our denominator. So here's the trick. So you're not allowed to square both sides. So most people want to say, oh, well, to get rid of a square root, you square it. That's true if you're working with an equation, which we know equations have equal signs, because when you have an equal sign, you can keep your equation equal by doing the same thing to both sides, right? We always know if you do it to one side, you do it to the other side. But if you're just looking at an expression, which this is just an expression because there's no equal sign here, you don't have two sides. So you have to keep it even. You can't just change the answer. So if I were to square this, the whole thing, it wouldn't be equivalent. The only thing that we are allowed to do, that we're always allowed to do, is we are always going to be allowed to multiply by 1. Because if you multiply something by 1, it doesn't change the number in any way. It's the same number. All right, well, you're probably thinking, well, how do I just multiply by 1? That's not going to make the square root of 5 go away. The answer is it does. You just have to be crafty. So in order to get rid of that square root of 5, I need to multiply it by itself, right? So I know that the square root of 5 times the square root of 5 is going to be the square root of 25, which is just 5. So then there's no more square root in the denominator, right? So if I multiply this by the square root of 5, then it'll be fine. Now, I said you're allowed to multiply by 1. Well, how can I make the square root of 5 equal to 1? The answer is I put a square root of 5 on the top of it and make it into a fraction. So the square root of 5 over the square root of 5 does simplify technically to 1. So I haven't broken any rules here. All right. So in order to get rid of it, I basically have to multiply top and bottom by whatever the square root is that I'm trying to get rid of. All right, so now I'm just going to go ahead, I'm going to multiply straight across. So that's going to give me 3 square root of 5. And then, like I said, the square root of 5 times the square root of 5 is just 5. So that is my number rationalized. So this and this, right, are equal to each other. If I had a calculator, which hopefully some of you have calculators with you, right? If you were to type in 3 divided by the square root of 5, hit enter, and then 3 times the square root of 5 divided by 5, hit enter, it gives you the exact same number because they are equivalent statements. One just looks prettier, I guess, than the other one. All right, so that's rationalized in the denominator. So those are all of your kind of major rules for radicals, sorry, all the R's. Okay, so now we're just gonna go through a couple examples and then we'll be done with this video. All right, so we have simplifying the following expression. So I'm gonna zoom in a little bit. There we go. Okay, so we're not gonna get to solving. We'll do that in another video. So we're just focusing on simplifying really quick. So we're just using those rules above to simplify these radical expressions. Okay, so number 1. Now there are a couple ways you can do number 1. You can do the rationalizing the denominator if you would like. You can also use that rule that we looked at where it says for division, you can create one giant fraction. I'm just going to do rationalizing for this one just because it seemed like it might be a little bit quicker, but there are a couple different techniques you actually could use for doing problem number 1. But like I said, I'm just going to try rationalizing my denominator to get that square root out of the bottom first. All right, so what that means is I'm going to have to multiply top and bottom by the square root of 20 because I want that square root of 20 to not be a square root anymore. This is going to give me 12. All right, now the square root of 2 times the square root of 20, this is multiplication. So I can combine these two radicals and by just multiplying the two numbers. So I'm just going to multiply 2 times 20, which is 40. So this is going to give me the square root of 40. All right, all over square root of 20 times square root of 20 is just 20. Okay, so now I have that square root out of the bottom of my fraction. Now I'm just going to kind of basically simplify. So first I'm going to look at the square root of 40 and see if there's any perfect squares that I can take out of that. And there are. 40 can be rewritten as 4 times 10, and 4 is a perfect square. So that's what I'm going to do. So 12. All right, and then I'm going to write this as 4 times 10 all over 20. All right, now, since 4 is a perfect square, I can kind of take it out as a 2. All right, you can write this in separate steps, kind of like we did above, where we rewrote it separately as square root of 4 times square root of 10, and then we simplified square root of 4. But I'm just going to do it all kind of in one step. So I know that the square root of 4 is 2, so I'm going to take this out as a 2. All right, so the 4 is coming out, and it's coming out as a 2. All right, so that means I'm going to multiply 12 times 2, and that's going to give me 24. I still have that square root of 10 because there's no other perfect squares that go into 10, all right, all over 20. All right, and there's one last thing I can do because 24 and 20 have a common factor. We can actually simplify 24 over 20 by dividing top and bottom by 4. So I'm going to divide 24 divided by 4 is 6, and 20 divided by 4 is 5. So for my final answer, I have 6 square root of 10 over 5. All right, and that is all the way simplified. All right, let's look at number 2. So right here for number 2, we know that we're allowed to combine terms if they have the same number underneath the radical. So let's see if I can simplify one of these and get them to be kind of the same number. So first we have 3 root 6. Well, the square root of 6 doesn't have any perfect squares that can be divided into it, so that one can't be simplified. So I'm hoping 54 can be simplified, and it can. So the square root of 54 can be rewritten as the square root of, let's go this way a little bit. So 3 square root of 6, remember we said that can't be simplified, minus 3 square root of 54. And 54 can be rewritten as 9 times 6. That's helpful because 9 is a perfect square. So just like in that first example, I had 4 times 10, 4 was a perfect square, so I could take out a 2. Well here, 9 is a perfect square. I can take out a 3, right? Because the square root of 9 is 3. So I'm just going to multiply the numbers out front. So this is 3 square root of 6 minus 3 times 3, which is 9. And I'm left with that square root of 6. Now, I have the same number underneath both of my radicals, so I can go ahead and combine the numbers out front because these are now like terms. So I'm just going to subtract 3 minus 9, and that's going to give me negative 6 square root of 6. There we go. And that is my simplified answer for problem number 2. All right, moving on to problem number 3. So this is a distribution problem, all right? And the reason why I picked this one is because the multiplication is actually kind of nice. The hard part is some students think that you have to multiply the number out front by the number underneath the radical, but that's not true. You're really just going to end up multiplying the radicals by each other. So first I'm going to distribute. So I have 4 times the square root of 5 times the square root of 15 minus 5 times the square root of 6 times the square root of 15. All right, and now since this is multiplication, I can go ahead then and combine the numbers underneath the radicals by multiplying them. So for the first one, I have 4 square root of 5 times 15 is, I think 75. 5 times 15, yeah, 75. Minus, and then I have 5, and then 6 times 15 is then going to be what, 90? Square root of 90. Okay, so that is how you would go ahead and multiply. So now I'm going to simplify the numbers under the radical. So the square root of 75, that can be broken down into 4 times the square root of 25 times 3, right? 25 times 3 is 75, minus 5, and then 90 can be broken down to 9 times 10. All right, so if this is taking you a bit longer to figure out which one of your perfect squares goes into it, that's okay. It could be you might need to do a little bit of guess and check at first to kind of figure out which ones are going to work. I usually start with the smallest one that I know and just work my way up, right? But yeah, so sometimes it takes a little bit of time to kind of get the hang of which perfect squares are going to go into your numbers. But yeah, once you get the practice down, it starts to get pretty quick. Okay, so so 4 square root of 25 times 3. So 25 is my perfect square. 25 is the square root. So the square root of 25 is 5. So I can take the 25, get rid of it, and move it outside of my radical as a 5. Over here, 9 times 10. 9 is my perfect square, so I can take it out as a 3. So I end up with 4 times 5, which is 20, radical 3, minus 5 times 3, which is 15, radical 10. Now that's as simplified as I can get this problem. 10 does not have a perfect square that goes into it. 3 does not have a perfect square that goes into it. So that is as far as I can go, which means I can't combine these two at the very end to make one radical, but I have simplified it quite a bit from where it started from. All right, last one that we're going to do in this video. So number 4, this is just a big kind of subtraction and addition problem. So what we're going to do is we're going to start this one by simplifying all of our radicals that we can. So square root of 12 can be broken down. So I'm going to do it over here a little bit. So this is negative 2, and then 12 is 4 times 3, 4 being my perfect square. All right, minus square root of 20. We've done this one before. This is 5 times 4. Again, 4 is my perfect square. All right, we'll go a little sideways. There we go. All right, and then plus 3 square root of 27, which is 9 times 3. All right, so now I'm going to go ahead and take all those perfect squares out. So 4 is the square root of 2. Square root of 4 is 2. And again, square root of 4 is 2. And for this one, square root of 9 is 3. So these are numbers that I'm able to kind of take out. Remember, you're multiplying to get when you get the numbers on the outside. So this becomes negative 4 root 3. This becomes negative 2 root 5. And this becomes 9 root 3. All right, so now I'm allowed to combine anything that has the same number under the square root. Which is this and this. So I have a negative 4 root 3 plus 9 root 3s. That's going to give me 5 root 3 minus 2 root 5.